Okay, perfect. So we kind of started this lecture last week, so I know we were kind of doing more of the calculations last week, and we kind of went through a good couple of questions there. Today is going to be very similar. I'm going to introduce kind of two new concepts for the calculations, but they are based on what we've already covered. So you're going to take the theory from the calculations that we've already done and use them in a different way. So we're going to be using them to work out solution concentrations, and we're also going to be looking at them in a titration-based setting. So taking your moles, taking your mass, converting it into moles using the molar mass, and then applying it to a lab practical that we're actually going to cover in one of our practical sessions. So I know I introduced this concept already, so we're going to talk about, so did that move on to theoretical yield? Everyone can see the theoretical yield slide, yeah?
Yeah, we can.
Perfect. So I'll just go over this once more, just because I know it was kind of rushed at the end of last week. So we often have exam questions based on what's called the theoretical yield. And what this is, it's the amount of product that the maximum amount of product that can physically form from a chemical reaction. So in other words, it's the amount of product possible as calculated using both your balanced chemical equation and what's known as a limiting reagent. Okay, so what that basically constitutes is the reactant that runs out first in a reaction. We won't go too much into how to determine the limiting reagent or anything like that, because most of the exam questions will be based on, they'll tell you what the limiting reagent is by saying that the other reagent is in excess. Okay, so whichever one is not in excess, that's your limiting reagent. So the analogy I like to use here is, like, and I mentioned it last week, is about the box of brownie mix and the eggs. That if you wanted to make a batch of brownies, you had one brownie mix kit, you needed 2 eggs for that brownie mix kit, but you have a carton of 6 eggs. Obviously, your eggs are in excess. Your brownie mix is the limiting reagent in that case, because you can only make one batch of brownies from that. So in the exact same way as a chemical reaction, one of these reactants is going to run out first, and we will have excess of one reactant left over that's not going to be used up. So I'll go through this example here that I have. Okay, so this is just the formation of water. And from the balanced chemical equation, I can see that we have 2 moles of hydrogen to 1 mole of oxygen. Okay, so your 2 stoichiometric coefficient there to 1 mole of oxygen forms 2 moles of water. For example, okay, so if I had done this reaction and I used much more in excess than what I needed of hydrogen, okay, so in this case I used 4 moles of hydrogen and I only use 0.5 moles of oxygen. So if I went into a lab, made up these 2 gases, 4 moles of hydrogen, 0.5 moles of oxygen, the ratio I actually used in that lab is 4 is to 0.5 or 8 is to 1 when you simplify that down, okay? If you compare that to what you actually need for that reaction, so based on its chemical equation there, you can see that hydrogen is far in excess of what we need, okay? So we only need 2 moles, but in actual fact, we have 8 moles there. So in that case, oxygen is our limiting reagent, and the oxygen will determine how much water is formed from that reaction. Okay. So I'll go through how we actually use theoretical yield. Okay, so we use this to kind of test the percentage recovery or an assay of a reaction. Okay, so if we were to go into a lab and make a product and we weigh that product at the end, we get an actual yield. Okay, so we have an actual experimental yield that we have, but we always compare that to what the maximum amount of product could have been, i.e., our theoretical yield. So doing an example here, okay, so if I take that reaction of water, okay, 2 moles of hydrogen, we have 1 mole of oxygen to 2 moles of water. We figured out from the last slide, okay, so oxygen is your limiting reagent in this case. So in this example, I use 0.5 moles of oxygen, okay? This amount is what's going to determine how much water is formed. So if I ignore my hydrogen there for 2 seconds, okay, because it's going to be in excess, it's not going to control the reaction. And I just look at the ratio between my limiting reagent and my product, which is water. Can everyone see that that ratio there is 1 is to 2? Okay, so 1 mole, if I had 1 mole of oxygen, it will form 2 moles of water. In my case, I use 0.5 moles of oxygen. The ratio is still 1 is to 2. So if I use 0.5 moles double that is going to form for water. So I'll actually form 1 mole of water. Okay. From there, then you convert it back into the moles to grams. So I'll do an example of this in a second, but it's very similar to what we've done in previous lectures. I have my 1 mole. I can get the molar mass of water based on periodic table of elements. And converting moles to grams, I can form 18 grams of water at most here. Okay. Say, for example, I completed that reaction then and I only formed 15 grams. So I should have formed 18. I only formed 15 grams. So my percentage yield becomes my actual, which is 15 grams, divided by my theoretical, which is 18 grams. So I actually have a percentage recovery or an assay there of 83.33%. Ideally, and in most cases, what you're looking for here is any upwards of 95% is almost like an acceptable yield. No reaction is ever going to go to 100% completion. It rarely happens, if ever. What we aim to do is have as much product formed as possible from that reaction because we control the conditions of the lab, we set the temperature, we set pH, we ensure that all the glassware is rinsed down, all of the reactants is involved in the reaction itself to aim for 100% recovery. It's not always the case. So in terms of this, what you'd see here is that, right, it's below the 95%. So something happened during the reaction that we ended up with product loss. So maybe not all some of the reactants may have stuck to the glassware and was then effectively removed from the reaction. We could have had, particularly for water, if a certain temperature was over 100 degrees, for example, we could have been boiling off or evaporating off that product, which led to a decrease in what we actually had at the end of that reaction. So it's a good way to test almost like reaction efficiency and how capable that reaction is of converting and forming a suitable amount of product at the end. So what I'll do now is I'll just switch over to the whiteboard. If you just wouldn't mind letting me, just 2 seconds now, we'll find it. Okay, can everyone see that whiteboard there? Perfect. Okay, so I have a question up here just on percentage yield. So I'm going to go through this now just so you can see how we actually calculate it. And this is taken from one of the exam questions, okay? So it's very similar to what you would expect in an exam. So what this states is how many grams of ammonia, so my NH3 there, can be produced from 16.5 grams of hydrogen, assuming an excess amount of nitrogen is available. Okay, so in this case, they tell you that nitrogen, or the N2 there, is in excess, which means your hydrogen is going to be the limiting reagent. So in this case, you don't focus on nitrogen, you only look at converting from the hydrogen instead. Okay? So we have an excess amount of nitrogen, so this means that there's more nitrogen than what is required to react with hydrogen. So we're only going to focus on hydrogen and my ammonia here. So this says if 84.3 grams of ammonia was produced, calculate the percentage yield. So in this case, what you're going to do is we're going to calculate the theoretical yield and then get that as a percentage or work out the percentage based on what we actually recovered. Okay. So first things first, okay, I'm going to convert that moles of H2 or my hydrogen there. So I'm going to work out the moles of hydrogen, okay? Sorry, I'll zoom in, so you can see it. Okay, so from the question, okay, I'm told that we have 16.5 grams of hydrogen. Okay, so based on that, I can actually work out its molar mass. Okay, so we're going to need the molar mass. Sorry, I'm just trying to make this text box a little bit bigger so we can see it. Okay, so the molar mass of hydrogen is probably the easiest one, okay, because we have 1 gram per mole per hydrogen atom. We're going to multiply that by 2 because we have 2 atoms of hydrogen. That's just going to give me 2 grams per mole. Okay, so we're given the mass in the question. We were told that we have 16.5 grams of hydrogen to use. We've worked out the molar mass is 2 grams per mole. So if I just show you the triangle over here then. Okay, so we have to work out the moles of hydrogen. We have our mass from the question. Okay, we were given that. We've worked out our molar mass. So if I cover what I'm trying to calculate there, so just if I cover over the moles, it tells me to divide 16.5 grams of hydrogen by 2 grams per mole. Can everyone see where I'm getting that from? Yeah. Okay, so I'm just going to work out the mass of hydrogen here, or moles, sorry, moles of hydrogen. Okay, so from the question, okay, so 16.5 grams, I divide that by 2 grams per mole, and it should give me 8.25. Okay, so I actually used 8.25 moles, well, not 82, sorry, 8.25 moles of hydrogen. Everyone okay with that so far, yeah? Okay, so in terms then of what we do next, okay, so I'm just going to move all this up so we have a bit of room. So your step 2 then is to look at the actual ratio based on your balanced chemical equation here, okay? So we're looking at the ratio between, because we want to know how much ammonia will form, okay? So hydrogen is our limiting reagent. So we're only focusing on the reaction or the ratio between H2, our limit reagent, and NH3. Okay, so if I were to look at that ratio then, just based on the balanced chemical equation, can everyone see that it's 3:2? Okay, so my hydrogen to NH3, my ratio is actually 3:2. Okay, so 3 moles of hydrogen will form 2 moles of ammonia if we used exactly what we needed and formed 100% of what we want. Okay. But in terms of what we used, we actually used 8.25 moles of H2. Okay, so we didn't use 3, we used much more than what we needed. So what you do here, okay, is that there's a couple of different ways you can do this. What I find easier to do is that if the ratio is 3:2, so I'm going to put that as like, that equals our 3 moles there, all right? I want to simplify this down. So I'm going to divide that by 3 to get it in as if it was 1 mole, okay? So what I'm doing here is simplifying the ratio down. Okay, so 8.25 divided by 3. So that should be, we'll say 2.75 moles. And then I multiply it by 2 to get that 3:2 ratio there. Okay, so that would be 2.75 moles multiplied by 2 because it's a 3:2 ratio. Okay, so I've tidied that up there just to get into 1 mole. So then all I need to do is multiply it by 2. And that will give me 2.75. So I should be getting 5.5 moles here. And that are my moles of ammonia that formed. So normally when it's kind of a little bit of an awkward ratio like that, say it's not as simple as like just multiplying or dividing by 2. I would just, whatever that ratio is, so in this case, you make that equal to what that is. divided by that number. So in this case, it's 8.25 divided by 3 to get 1 mole equivalent, and then multiply it by 2 to get that 3:2 reaction. Okay. Everyone okay with that so far? Does anyone have any questions on that part, or is that okay? Okay, perfect. So what I'm going to do now, so we have our moles, okay? Our yield is always going to be done in, sorry, no, our yield is always going to be done in
Sorry,
grams.
yeah. Could I ask
Oh, sorry, yeah.
a question? Yeah. So you've gotten 3:2 there because the H3 is gone over to the other H2 there, and you have less one. Is that it? That's 3:2.
Yeah, so if I look at my balanced chemical equation that's here, okay, so
Yep.
my hydrogen is my limiting reagent, so 3 moles will form 2 moles of ammonia, okay? In this case, I didn't use 3 moles and I didn't form 2 moles, so I have to work out that ratio of what I actually used.
Okay.
So what I did was I took what I had, so 2.5 moles,
Yeah.
divided it by 3,
Yeah.
then got the 1 mole equivalent, and then multiplied by 2 to get that 2 moles equivalent.
Okay.
So that's what I write there. So it's not actually one, it's like if 1 mole equivalent if 1 mole was used.
Okay.
It just makes the kind of conversion of that ratio a little bit easier.
Yep. Thank you.
It's no worries at all. Okay, so in that case then, as I said, the yields are always done in mass. Okay, so we have a mole amount here. So I need to get the mass of NH3 now. Okay, so I have a mole amount. I need to convert it back using the molar mass. So we'll do a little bit of practice on the molar mass of nitrogen here. Okay, so as you can see, it's kind of the same concepts that we've already done, but it's just kind of being used in a different way each time. Okay, so it's the molar mass of NH3. So we have 1 nitrogen, which is 14 grams per mole on the periodic table. And we only have 1 atom of nitrogen in ammonia, but I'm just going to include the 1 there. Okay. For hydrogen then, so hydrogen is 1 gram per mole. And I'm going to multiply by that because we had 3 atoms of hydrogen per 1 mole of ammonia. Okay. So adding all those up together, so it should be 14. So 1 by 3 is obviously 3. So 14 plus 3 is my 17 grams per mole there. So if I just come back here just for 2 seconds for that triangle. Okay, so in this case, I'm working at the mass. Okay, so just pretend I'm covering that mass there. I have a mole amount. I've just worked that out. I've just worked out the molar mass. So if I cover mass, it tells me to multiply the moles by the molar mass. So that's exactly what I'm going to do now. So I have that mole amount. I have my molar mass. So to work out the mass, the mass of NH3, I'm going to take that 5.5 moles and I'm going to multiply it by the molar mass. Okay, so what you should be getting here then is 93.5. Is that okay? Everyone happy enough with that, yeah? Okay, so I'm just going to review the question then up here, okay? So that's how many grams of ammonia can be produced if we use 16.5 grams of hydrogen, okay? So that's our theoretical yield for that reaction, okay? Because we took the mass of the limiting reagent, converted it into moles using our molar masses, looked at the ratio between them, and then converted back So what this actually represents here, that 93.5 grams, is my theoretical yield. So more often than not, what they'll say in the question, they'll ask you to work out the theoretical yield, and then it will give you a certain amount that actually formed. Okay, so in this case, someone completed this reaction and they formed 84.3 grams of ammonium. So now we need to work out the percentage yield. Okay, so I'm just going to call this like step 4. Okay, so this will be percentage yield. I'm just going to write this down. So our percentage yield, okay, is our actual yield over a theoretical yield multiplied by 100. We were told then in the question, okay, so percentage yield. So we were told in the question that when someone did this reaction, 84.3 grams of ammonia was formed. We've worked out our percentage yield as 93.5. Okay, so that's my actual over my theoretical. I'm going to multiply that by 100 for my percentage yield. And what we should be getting here is 84.3 divided by 93.5. Yeah, so we should be getting around 90.16% here. So it didn't ask it in this question, okay, but as you can see, right, from what I've said before, that 90.16 is kind of below the accepted percentage recovery for most reactions, okay? So ideally, you'd be looking at any percentage recovery above 95%. So more often than not, they follow up in the exam question that, okay, you recovered 90.16 of your theoretical yield of your product. What might have gone wrong during the reaction, or where might product loss have occurred during the reaction? So we'll cover that kind of more so when we talk about the labs, because it will kind of become more clear when we're actually doing an experiment where this is involved. But it's just to let you know that that's how typically how the exam paper format goes. They'll ask you to calculate theoretical yields, give you a certain mass that formed, then it will be over your theoretical yield that you've just worked out, and then they'll ask you to comment on that percentage yield then. Is that okay, guys? Okay, perfect. So I'm going to exit out of this now, and I'm going to go back onto slide deck. Perfect. Can everyone see that okay then? Okay. So from here, then we're going to start talking about solutions. Okay, so more often than not, we're going to be using chemical reactions that involve a solution of a certain concentration. So we'll get started on actually what is a solution. Okay. So solutions are defined as a homogeneous mixture of two or more pure substances. Okay. More often than not, you'll have one substance that's dissolved in another substance, i.e. the solvent. Okay, so if you were, say, to make up a salt solution, your water would be the solvent there. It's present in the greatest abundance. Okay, so you have much more of your solvent than your solute. In that case, your NaCl would be the solute in that case, of whatever is dissolving in the solvent. But the two of those combined, they are both pure substances. Your solvent is your water, present in greatest abundance, and then anything that's dissolved in the solvent is called a solute. So where this actually kind of comes into play then, okay, so it's a little bit about how a solution forms. So when we have an ionic substance, so I'm going to use NaCl or table salt as a common example here, okay? That when we add salt into water, what happens is the solvent or the water molecules start pulling apart individual ions from the crystal or the salt crystal and start solvating them. So what this means is that if we had almost a clump or a crystal lattice of salt here, okay, so Na plus and Cl minus, When we add that to water, what happens is that we have individual solvent or water molecules that will surround each of the ions. Okay, so in this case, it would be your Na or Na plus or your Cl minus. They will surround each one of those ions and form almost like a loosely bound complex around them. Okay, so if I were to take this example here, it would look something like this if you were to look at it at a molecular level. So Na plus, okay, so we talked about this when we were talking about kind of differences in the bonding. Okay, so Na plus and Cl minus, they form an ionic bond. So what happens in water is that, and water is that kind of partial positive and partial negative charge that we talked about during lecture 3. Okay, so I put a little bit of a reminder there. But water possesses some degree of electronegativity. Okay, so those red circles there represent oxygen, and those two white circles represent the two hydrogen atoms. Okay, what happens is that your oxygen is much more electronegative than your two hydrogen atoms there. It will draw the electrons that are involved in the water bonds towards itself. Okay, so it gives it that partial negative charge. Your two hydrogen atoms there will be left with a partial positive charge because the electrons are being dragged away from it. Okay, so they don't carry as much of a negative charge as the oxygens would. How this happens then is that your Na plus, obviously that's a formal or a complete positive charge. The negative ends or the polar negative ends of water will start to align themselves with that. Okay, so you can see that there, the partial negative charges are almost aligning with that that positive charge in the center. The reason why salt dissolves in water is that NaCl, so that ionic bond between them, these reactions are much stronger than the ionic bond that exists between Na and Cl. So in other words, these bonds that form here are much more capable of pulling NaCl apart and solvating each individual ion than it is to have NaCl exist in water as NaCl. So basically these bonds predominate when NaCl is dissolved in water. Okay? Is everyone okay with that? Everyone can see where I'm getting that information from. Okay. So what that process is called is basically it's called dissociation. So your ionic bond will break apart or dissociate in water based on that difference in electronegativity. And these electronegative charges are stronger than the ionic bond, and they will pull apart that crystal lattice that's formed in an ionic bond. Where this comes into play then is when we talk about electrolytes. Okay, so an electrolyte is any substance that undergoes dissociation. So any substance that carries out this process when it's dissolved in water is what's known as an electrolyte. So we're going to come across, so I used NaCl as an example here. We're going to come across in the labs, we're going to be using hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base. Okay, so what we will see is that strong acids and strong bases will dissociate in water. So they will undergo this breaking apart and dissociation in water like this. Whereas a non-electrolyte won't dissolve in water. So they may dissolve in water, but they won't dissociate into ions when it does. So things like ethanol or sugar molecules, they will dissolve in water, but they'll maintain their original structure or that original bond that they had. Electrolytes will completely dissociate into their respective ions when they're dissolved in water. Where this comes into play and what we're going to be looking at is that if you think about if NaCl dissociates in water, let's go back here a second, Na plus exists as a positive charge. Its counterpart then, chlorine, is Cl minus, and that carries a negative charge in solution. Okay, so they're existing in solution as Na plus and Cl minus. They're highly charged, okay, and they're a lot more mobile. So if you think about it, if you had something in solution that was kind of more bulky or heavier like this, that was very strongly bonded together, versus how they exist on their own when they dissociate, their ions are much more mobile. Okay, so they can move a lot freer in solution than they would if they were in this kind of crystal lattice structure, because they're almost stuck together in a huge clump, for example. when they're in this crystal lattice structure. But when they dissociate, they form their Na plus Cl minus, and they're a lot freer and a lot more mobile. Where this comes into play is that when they carry charge and they're mobile like that, so they can kind of freely dissociate and move in solution, electrolytes can carry an electrical charge, okay, because they're charged and they can move freely around solution much quicker than they could in their crystalline lattice structure, like we see here. Okay, so we will be looking at things like that in the lab, but it's just to note that electrolytes are capable of carrying an electrical charge, whereas non-electrolytes don't, okay? Because they don't dissociate when they're added into water or into solution. Okay, so kind of more classification than I suppose then. So you have your electrolytes and your non-electrolytes. And what we'll come across are the strength of electrolytes. So you can actually classify them further again based on how strongly they dissociate when they're in solution. So for example, okay, a strong electrolyte, so things like our hydrochloric acid, it's a strong acid. When they are dissolved in water, they will completely dissociate. Okay, so no hydrochloric acid will exist in its molecular formula as this. When hydrochloric acid is added in solution, it will instantly dissociate into H plus and Cl minus. So none of it will exist in its molecular formula. On the other hand, then we have weak electrolytes that only dissociate partially when they're dissolved in water. Okay, so we have things like acetic acid or common vinegar. Okay, its molecular formula is CH3COOH. It will undergo some dissociation to some extent. Okay, so it will split into that CH3CO minus and its H plus, but more often than not, it will remain in its undissociated form, as over here. Okay, so it will remain as so. Some of it will dissociate into its respective ions, but never to the same extent as what we'd see with a strong electrolyte. So you can kind of see a good example in this diagram here. Okay, so as we talked about a non-electrolyte, okay, so it doesn't contain ions, it doesn't dissociate, so it can't carry an electrical current. So there's kind of a simple experiment we could set up that we have as an ionic or a non-electrolyte solution. Okay, so we have that in water, and we see if it can conduct an electrical current to some extent that it would light up a bulb. For a non-electrolyte, because they don't contain ions, it won't dissociate. We should never see the bulb light up, okay, because there's no electrical current flowing through that solution. If I were to show you maybe a weak electrolyte, okay, so in this case, like our acetic acid here, some of it will exist in its respective ions, okay, so some of it will dissociate. So we should see a small glimmer of light from that because an electrical current will flow, but just not to the same extent as we would see if we added a strong electrolyte. So something that dissociates completely into ions, all of it exists as its ions, and they're all available to conduct an electrical charge. Whereas in a weak electrolyte, some of them do, but it mostly stays in its unionized form, so we don't see it to the same extent. Is that okay, guys? Perfect. So where this comes into play then with solutions. So what we look at is that it's helpful to kind of pay attention to exactly what species are present in a reaction mixture. Okay, so we talked about this when we looked at the balanced chemical equations. You can often have an S that represents that it's reacting as a solid, L for liquid, G for the gaseous state or gas, and we often have AQ that it's made up of an aqueous solution. Okay, so we'll see this during our lab practical sessions and kind of in some of the questions that we'll cover later on. But it's helpful to pay attention to that, okay? Because the rate of the reaction or how quickly reactants, and we'll get to this when we kind of talk about the rates of reaction, so I won't go into it too much, but each of these have different rates of reaction associated with them. Sometimes reactions are processed at a quicker rate when we use a gas rather than a solid. Okay, so just to introduce it now, it's just helpful to pay attention to that. What also affects the rate of the reaction is how concentrated a reaction mixture is. Okay, so if I had a solution that was incredibly diluted. Okay, so I have very little solute in a huge amount of solvent in comparison to a much more concentrated solution where I'd have a lot or a huge amount of solute in the same amount of solvent. The reaction is going to occur an awful lot quicker in the concentrated solution than it would in the dilute solution because there's a lot more reactant molecules present that are very, very close to each other in the concentrated solution. So there is much more of a chance that they'll combine with each other and react. If I put a very small amount of solute into a given amount of solvent, it obviously there's not as much per, say, per mil of that solvent there. So it won't happen as quickly as it would in a concentrated solution because the molecules are very far apart. They have to collide with each other for a reaction to occur, and that won't happen as quickly as it would if it was in a concentrated solution. So what concentration actually refers to is that it's the quantity of a solute that is dissolved in a given quantity of solvent. So say, for example, I had 500 ml and I added 0.5 grams of my solute in. Okay, that would be a very small amount of solute in quite a large volume of solvent. A concentrated solution then is the exact opposite, so that would be a large quantity of solute in the same amount of solvent. So in this case, a dilute would be 0.5 grams of, say, NaCl in 500 ml. My concentrated would be 20 grams in 500 ml. Okay, so just it all depends on the amount of solute that is dissolved in a given amount of solvent. So where we actually have this then is that we express concentration as molarity. So two solutions can have the same compound in it, like I just described, okay? So if we had a dilute solution of NaCl, where we have 0.5 grams in 500 ml, I could have another solution on my right that is an NaCl solution, but it has 20 grams of NaCl per 500 ml. In that case, we have two solutions that contain the exact same thing, but we have two different proportions of the compounds that are within that solution. And of course, as chemists, we relate that back to the amount, it's the moles of a solute in a given amount of solvent. Okay, so what molarity actually is it's an expression for concentration. Okay, so we convert any of the grams of a solute into moles, and we express that moles per liter of solvent. Okay, so how we'd actually normally do this, and I hope this works. Let me see. I don't know if that will actually, doesn't seem to be playing for me. We'll cover this in the lab anyway. But what you would actually do, I suppose, in the procedure to work out a solution of like known concentration or molarity here, is that you would weigh out a given mass of a solute. So I'll use the NaCl example here. If we had an NaCl solution, we would weigh out a certain amount of that NaCl, convert it to moles using its molar mass. So the very same way we've done the calculations previously. We add that massive solution into what's known as a volumetric flask, okay? So you may have seen this before, that it's a round-bottomed piece of glassware, okay? It's not very clear on this video here, but there's a line, what's called a meniscus, around the top, kind of halfway up the neck of a volumetric flask. Once the liquid or the solvent sits on that line, so you'll see almost like, it's called a meniscus line. So you'll see the bottom of that liquid sit on that line. What that means is that you have created a solution of a standard given volume. So each one of these volumetric flasks, they range from 25 ml up to 2 liters. But once you make a solution and you fill each of those volumetric flasks to that line, you have made a solution of that given volume. So it's very, very precise. I think they have a percentage uncertainty or percentage error of maybe 0.02 milliliters. So basically what you can say for sure is that if you made up a 250 ml solution with a volumetric flask, is that you know for sure that you have just made a solution of 250 ml. It's not open to interpretation, I suppose. You've delivered an exact volume of a solution. So what you do is you take your solute, okay, so you'd weigh it out based on that moles to mass ratio. You'd add the solute into the volumetric flask. You'd invert it to dissolve solute in the solvent, and then you'd make up to the line on the neck of the flask with the solvent of choice. And then you have a standard solution of your solute. Okay. So guys, what I'll do now, okay, because it's just gone 6 o'clock, so I know that's there's a lot of information there. So I'll pause here for maybe just 5-10 minutes because we're going to go into kind of more calculation based for the molarity. So if you want to just take 10 minutes now, we'll come back and then we'll kind of delve into some of the calculations that are involved in this. Is that okay?
Perfect. Thanks.
Perfect. Right. See you in 10 minutes, guys. Okay, can you guys see that okay?
Yep.
Yeah.
Okay, so I suppose to make up solutions, okay, so it wouldn't be, I suppose, very efficient in a lab, and it wouldn't be the best practice that if you needed a series of different solutions at different concentrations, that you would be running over and back to the balance, kind of weighing out maybe say 5 grams of NaCl for one solution, coming back and making the concentrated solution, having to weigh out a different amount to make up a different solution. So the way it's normally done is that you would prepare a very concentrated stock solution. So one solution at the very start that's like a lot higher concentration than the rest. And then you would deliver a known volume of that solution into new volumetric flasks to make up a series of dilutions. Okay. So it kind of prevents that whole running back and forth with the balance, weighing out different amounts. You take one stock solution and through volumetric analysis, so we're definitely going to cover this in the labs, but using volumetric analysis, you can actually prepare a series of diluted solutions from just the one stock solution. Okay, so a lot less waste, a lot less kind of time constraints in the lab. You can make up one and kind of make a series of solutions from that. So how that's done, and this will make a lot more sense when we actually do it in the lab, is that we make up a solution very similar to the calculations we've just done there. You'd make up a stock concentrated solution. You would then take a pipette. So what looks like this, okay, so it's very similar. It's a volumetric glassware. So your pipette is almost like a long thin glass bulb, for example. And they each deliver a known volume of a solution. So in the exact same way I described the volumetric flask, it has a line on the neck of the pipette, which represents that's the standard volume that would deliver. So you would take that pipette to deliver a set volume of the concentration solution to a new volumetric flask. So similar to what's been done here, they made up a stock concentrated solution. They took a 25 ml pipette to take a known volume of that solution out into a new volumetric flask, and then made that up to the mark or the meniscus with whatever solvent they were using. Okay, so you can kind of see in the two different color changes that my solution on the right there is very highly concentrated. I took a certain volume of that out, made it up to the mark with deionized water or a solvent, and the color change would indicate that that's a much more dilute solution than what's on the right. Okay, so a lot more concentrated here, much more dilute on the left. So what we'd actually do here is to work out, because obviously the stock solution is going to have one concentration. We can work out the molarity or the concentration of my new solution or the dilute solution using this calculation here, okay? So it's simple as have your concentration, your molarity or your concentration of your concentrated solution, the volume you pipetted out of that solution, so in this case it would be 25 ml in this example up here, and that's actually equal to the molarity of your dilute solution. So normally this would be X, you're trying to find what that is, and then the total volume of your dilute would be the volume of your volumetric flask that you used. So for example, if that was 250 ml, your new solution is made up to 250 ml, so that would be your total volume of the dilute. So in saying that, they look a little something like this. Okay, so what you'd have is they normally give you some information about a concentrated solution that was prepared. They took out a certain, so that you either have to work out the volume that was pipetted out or the molarity of your new solution. So I've kind of color coordinated it here. So what volume of a concentrated 12 molar hydrochloric acid solution, okay, so incredibly concentrated hydrochloric acid solution, must be taken to prepare a 750 ml solution of 0.24 molar hydrochloric acid. So we would take our dilution calculation there, fill in what we know. Okay, so in this case, I know the concentration of my stock standard solution. Okay, so that would be my 12 molar there. It's asking me what volume of that I took out. So we just call that X, or that's what we're trying to work out. And that's equal to the molarity of your new solution. So the much more dilute solution of 0.24 molar. And you're going to multiply that then by the volume of 750 ml. Okay, so that's your new solution volume, your new dilute concentration, the original concentration, what we were working with, and then we just need to work out what was taken out. So we leave that on its own. So we'll leave that and move everything across the equal sign. So you'll see that the 0.24 molar and the 750 ml, that stays the same on the right hand side. And my 12 molar there moves across the equal sign to divide on this side. So it actually works out as 0.24 molar multiplied by 750 ml divided by 12 molar. So putting all that into that calculation, you end up taking 15 ml of that solution out to prepare your new one. Is that okay, guys? Is that making sense? Is there any part of that you want me to go back over? Okay, so what I might do is I have an example of this as well. So I'm going to stop sharing the screen here and then just pull up the whiteboard again. Okay. So again, you'd have something similar to this in an exam. Okay, so you were working in a laboratory and you were handed a 0.5 molar stock solution of KMnO4. How would you prepare a 0.1 molar and a 0.02 molar solution of KMnO4?
Sorry, is that equation, will that be given to us at the exam? Or
No, I wouldn't think this would be given in the
Grant?
exam.
No, I
Okay?
thought it was just included in the question there from an exam. No, that's fine.
Yeah, so I think most of the moles to mass conversions and things like that, so your dilute calculation and then your titration calculation won't be given in the exam.
Okay,
So it's more
good.
just your periodic table of elements and then any kind of additional equations you might need.
Good.
Okay, so we're going to fill in what we know here. Okay, so in this case, we're working with a 0.5 molar stock solution of KMnO4. Okay, so the 0.5 molar that's listed there, that's my molarity of my concentrated. Because that's the solution I'm starting with. It's going to be the most highly concentrated one out of what we have to prepare. We need to know how to work this out. Okay, so I'm just going to leave. We don't know how much of that was pipetted out, okay, because we're preparing those solutions. So that's going to be X for my volume of my concentrated. Your molarity of your dilute then, in this case, we'll do the first one there, so 0.1 molar. And then it actually doesn't tell you, and this is kind of unusual, that the total volume of your new dilute solution. If it doesn't tell you a volume here, just assume you have 100 ml. Now, more often than not, you will be given volumes for your new dilute solution. So they'll tell you, similar to what I just did, they'll tell you that you'll make up 500 ml or you'll make up 700 ml, for example. In this case, it didn't. So if it doesn't, just assume you have 100 ml. Okay, so for this then, we're going to get X on its own because we don't know what that is. We don't know the volume that's pipetted out to make these new dilute solutions. So in that case, I'm going to leave the right-hand side in the same way. And I'm going to bring that 0.5 molar across the equal sign to divide on my right-hand side. Okay, so it's multiplying on the left. If I bring that over the equal sign, it will divide. So my volume that's pipetted out will now be 0.1 by 100 ml divided by 0.5. So that tells me that 20 ml. Okay, so 20 ml of that 0.5 molar stock solution was taken out of the stock solution, put into a 100 ml volumetric flask. The 100 ml flask was then made up to the mark to give me a set volume of 100 ml. And that's what I used to make up that 0.1 molar. All right. So in the exact same way then, that if you had to make 0.02 molar, okay, so it would look something like this. It'd be the exact same calculation, but instead of 0.1, it's 0.02 molar, so much more dilute again. So that would be 0.02 molar multiplied by 100 divided by 0.5. So in that case, to make the much more dilute solution, you'd only need to take out 4 ml. So which makes sense, okay, is that, and you know you're on the right track, that if you prepare one solution and then a much more dilute solution, that the volume of the stock that you take out should decrease, okay, because you're not taking as much of the solute concentration with you into the new dilute solution. So if the solutions are becoming more dilute, it would make sense that the volume of the stock that you take out should also be decreasing. Okay, so in this case, we had 20 ml and then 4 ml. Is that okay, guys? Everyone happy enough with that so far? Okay, so I'll stop. I'll just switch back again. Okay, perfect. Yeah, so this is kind of like a diagram that describes how we actually take each one. So we've kind of worked out through this already. So I won't go too much into this, but what we can do, and we've practiced it kind of in the last 2 lectures now, is that you can work out with a reagent. Okay, so we'll call A our reagent 1. You can convert reagent 1 into moles of reagent 1 or reagent A using the molar mass. Okay, so very similar to what we've done. You can work out the stoichiometric coefficient, so that's the ratio with the balanced chemical equation between A and B, and then we've often converted it back then to grams of B, or reagent 2, or product 1, for example. So we can actually start with a reagent, convert it into moles, look at the ratio between them to get, say, moles of B or a product, and then finally convert it back into a gram amount. What you don't see there is then you can work out percentage yields from here. You can also work back the way, okay? So you could actually start out with a molarity of a solution. We could convert it back using our volume in liters and to get our moles, and then work that back out into grams. So this kind of shows a really good kind of interconnection between the kind of mass to moles conversion, or we could actually work back the way from a solution of that solute or of that compound to end up with the grams amount at the end. So it's all very interconnected on how we work back the way. So where this all comes into play then is one of the lab practicals we're going to do, and it's working with a titration. Okay. So what a titration actually is, it's a very quantitative analytical method. So what we can do is that we can work out, we have one reagent of a certain concentration. We know its volume, we know its concentration based on what we did or what we prepared. We can take the volume of that concentrated solution that reacts and basically work out the concentration of a solution that's unknown. Okay, so kind of along this concept here, we can take a known concentration of reactant A, for example. We can react it with B, take the volume of A that reacted with B to eventually work out the concentration of B here. Okay. So kind of going through this, we use a known volume of solution with a known concentration. So we prepare this in a lab and we conduct a titration. And then we react it with a solution of unknown concentration. We record the solution of unknown concentration that it took for a change to take place. Okay, so normally with the types of titrations we're going to be looking at, we're going to add what's called an indicator. So as you can imagine, most of the chemicals that we work with are colorless. Okay, so once they react, it's very difficult to see an endpoint of that reaction because it's only going to form a colorless product. In this case, we can add what's called an indicator that changes it changes over a certain pH range or a certain type of reaction. And when that change happens, the indicator changes color. So we can visualize the endpoint of a reaction. We take then almost like a snapshot of the volume that was used to make that change occur. And then we can work back to calculate the concentration of the unknown. Okay, so what we're going to do in our labs is that we're going to use an acid and base titration. So we're going to be looking at a hydrochloric acid and a sodium hydroxide titration. And we're going to be working out the concentration of sodium hydroxide based on using a standard concentrated solution of hydrochloric acid. Over the course of an acid and base reaction, the acid will neutralize the base to form a salt and water. Okay, so I'll go through this a little bit in greater detail when we actually do the practical. But just for now, when an acid and base react with each other, they essentially neutralize each other to form a salt and a water. What that brings about is a significant change in pH. And as I said, we use indicators to visualize that change because what indicators do is that at one certain pH, they're one color. And when we reach that threshold or the endpoint of a reaction, the indicator will change color and we'll be able to visualize that endpoint and then mark the volume that was used to reach that endpoint. Okay, so it's a very easy way to concentrate or work out or calculate, I should say, the concentration of an unknown. And it's a much more like visual reaction that we can conduct here. So from the end, so at the end of a titration, so this is how we'd actually work out the concentration of the unknown here, okay? So we can work out, for example, if we were doing a reaction between sodium carbonate here and hydrochloric acid. So I've color coded this just based on where each of these figures are coming from, okay? So we were given this example and we were told to calculate the concentration of a hydrochloric acid solution that was titrated against 25 centimeters cubed of a solution of known concentration. So in this case, it's 0.05 molar. And we'll work that out in moles per litre and grams per litre. Don't worry about this too much. I just want to show you where each one of these are coming from. So in this case, the 25 centimeters cubed and our 0.05 molar concentration there, that's our known concentration. We have a known volume and a known concentration. Okay. So we can put that into a titration reaction. Okay. And we're going to start reacting it with hydrochloric acid. So we'll pretend this was done. So we'll have a solution with our 25 centimeters cubed of 0.05 molar sodium carbonate in it. Over the course of titration, we'll be titrating it with our HCl. We don't know the concentration of that yet. But what we can visualize is the volume that's been added into that 25 centimeters cubed. So we do titrations normally 3 times, okay, and we get the average of three titrations to give us our average titer value. It's a much more accurate representation of where that endpoint actually happens. So, for example, the first titration, it took 22.2 centimeters cubed of hydrochloric acid to visualize that color change. The second titration then, so it's a little bit over, but 22.7 centimeters cubed or mil of HCl was needed to visualize that color change. And then your third titration, 22.6, was needed to visualize the color change. So what we can say is that on average, it took 22.5 mil of HCl to evoke that color change. Where this all comes into play then is that we're obviously looking for the concentration of HCl up here. And we have what's called a titration equation. Okay, so you have your molarity of your acid. The molarity of your acid is what we're looking for. That's the concentration of the acid. The volume of the acid is whatever was used during the titration to evoke that color change. Okay, so that's your 22.5 centimeters cubed there. That's the average volume that it took to cause that color change in the reaction. Your molarity of your base then, so that's what we were given at the very start, so 0.05 molar. And we prepared 25 centimeters cubed of that. So we delivered a known volume of a known concentration here. So that's what we know. At the end of these then, so we also take into account the balanced chemical equation. So this is kind of like an all-encompassing calculation, for example, all right? But you'll always take the coefficient of acid and the coefficient of base from its balanced chemical equation, okay? So what we essentially say here is that 2 moles of hydrochloric acid, will react with 1 mole of sodium carbonate. Okay, so 2 is to 1 there. And that's what I've inputted down here for coefficient of acid and coefficient of base. Is everyone okay around getting each one of these from so far? Does anyone have any questions on any of those figures? No? Okay. Okay, so just continuing on that concentration then, okay, so we have our balanced chemical equation here, and similar to what we had in our dilution calculation there, we're trying to get X on its own. So what we have here is that we've just moved everything over to the right-hand side, okay, we're trying to get X on its own, we're trying to find out the concentration of hydrochloric acid. So I've moved everything over here, and I can work this out just putting it into a calculator, all right? So what we essentially end up here is that we bring up our, we bring up our stoichiometric coefficient across the equal sign, okay, so to multiply on top. We bring down our average titer volume across the equal sign so that it ends up dividing on the right-hand side. So that's where this is kind of tidied up to. And inputting all of that into a calculator, we'll end up with 0.111 molar. So all in all, what we've ended up with is that we've worked out the concentration of hydrochloric acid based on using a known volume of a known concentration of a solution, and then using the volume that reacted with that known volume of a known concentration to work out our concentration of our acid there. So what I'll do is so that's again the end of the presentation there. So what I'll do is I'll swap over to the whiteboard and we'll just do one of those calculations out together just to finish off our titrations. So the whole theory behind the titration I'll go into much more detail with when we do the actual experiment, because I find it much more easier to visualize when I have the glassware in front of me. So I'll just focus on the calculation for now, and then we'll kind of conduct the theory of it then when we get to the labs. So our exam questions for our titrations tend to look like this, okay? So we have a standard solution of 0.1 molar HCl. So we titrate that against 20 ml of an unknown solution of sodium hydroxide, using methyl orange as an indicator. So the indicator will significantly change colour at a certain pH, so that's what we can use to visualize the endpoint. It was found that 30 ml of 0.1 molar HCl was required for neutralization. So we need to work out the molarity of your sodium hydroxide based on that information. Okay, so we just take down what we know first. We even highlight what we know here. Okay, so that's 0.1 molar HCl. Okay, so that's your concentrated solution that we know the volume of. Okay, because we used up 30 ml of HCl. Okay, so we have a known volume and a known molarity of hydrochloric acid. We don't know, we're looking for the concentration of sodium hydroxide, so we'll leave that blank for a moment. But we know that we titrated that against 20 ml of an unknown solution of NaOH. So I can input everything I know into the titration equation based on its balanced chemical equation as well, and I can end up with finding the molarity of my sodium hydroxide. All right. So I'm just going to input everything I know here. Okay, so my molarity of my acid that I use, so that's the known concentration. That's 0.1 molar, and that's coming from the HCl. All right. In the question then, it told me it took 30 ml of my HCl there. Okay, so that's 30 ml. My coefficient of my acid then, so that's where I'm going to look to the balanced chemical equation. Okay, so this one is simple enough because it's just a 1:1 reaction. I don't have any stoichiometric coefficients I need to take into account. If there's no number there, that means it's a 1:1 reaction. Okay, so it simplifies this an awful lot. My molarity and my base then, so I don't know that, that's what I'm trying to calculate, so I'll just list that as X. My volume on my base, so in the titration, I use 20 mil. So that's what I'm going to input there. And my coefficient on my base then, again, it's a 1:1 reaction, so I'll just put that as 1. Is everyone okay with that so far, guys? You can see where I'm getting those figures from.
Yeah.
Okay, perfect. So I'm going to get rid of the ones here, okay? Because if you bring a 1 up to multiply or divide, it's obviously just going to give you the same amount. So if it's a 1:1 reaction, you can essentially you can cancel out the coefficients, okay? Because they're not going to be involved. Okay, so what I'm left with is something that looks like this. So I'll go through a lot of these examples when we're in the lab. I just wanted to show you where the basis of these are coming from. So to get X on its own, I'm going to take that 20 mil. So it's multiplying on the right-hand side. If I bring it across the equal sign, it will divide on the left-hand side. Okay, so in this case, then it will be my X on its own. So I'm just going to input all that into the calculator. Okay, so it's going to be 0.1 molar multiplied by 30 mil and then divided by 20. So what I should be getting here is 0.15 molar. And what this is, it's my molarity of my NaOH. Okay, so that's your final answer for that one there. So basically when we did this titration, we took 20 mil, so that's our known volume of an unknown solution. So unknown solution means we don't know its concentration. We put that into our conical flask. Our 0.1 molar HCl, we know the concentration of, and through the titration, we can work out how much volume of that acid we needed to react with the 20 mil of NaOH. And inputting all of that data into my titration equation, I can figure out what my unknown molarity is there. Is that okay, guys? Everyone happy enough with that so far anyway? Okay, well, if it's any good news, I promise that's like the last set of calculations we're going to do. So you've navigated through stoichiometry. That's as bad as it's going to get. So at least it's over and done with. So what I'm going to do is I'm going to stop sharing the whiteboard. Spare me 2 seconds. So again, things like that will make an awful lot more sense when you see them being done in the lab, okay? Because you'll be able to see the glassware, see that it's delivering a certain volume of solution. We'll be making up solutions in the lab, and then we'll be using them in the titration. So an awful lot of this will start to make sense when we can physically see it in the lab, I suppose. So just speaking of the lab, so what the plan is that we're in the lab on the 18th of October, so this Saturday coming, and we're also in the lab then on the 25th of October. So the way these sessions are done is that they are a 9 to 5, okay? So we will be in the lab for most of the day, but we'll be doing 4 different experiments on each day. So on the 18th of October, we're starting off with a calibration of a balance experiment, okay? So we'll be able to, it's basically a GLP exercise. We'll be able to see what affects the mass reading when we place like a beaker of salt or a beaker on its own under certain conditions. So if we handle it, or if we put it into an oven, or we leave the door of the balance open when we're weighing, what we can see the mass fluctuations based on that, and we'll be able to see the effect of each one of those on the mass that we record. So it's essentially what we have to take into account when we're taking an accurate mass reading. We'll also be doing calibration of a pipette. Okay, so we'll be dispensing a known volume using different types of pipettes and basically converting the volume back to mass and seeing how accurate we were to deliver a known volume of a pipette. As you can see, the volumetric glassware is designed to deliver a set volume. So if we have any mistakes kind of in the delivery of a volume, it can seriously affect the concentration that we calculate. So we want to make sure that when we're delivering a known volume, that we all know how to deliver that known volume, and that we're not overestimating or underestimating the volume that we deliver. From there, then we'll be doing kind of a percentage of sand in a sand and salt mixture. So we'll be using kind of mass balance analysis for that. So that will make more sense when we kind of do the fluctuations in mass for the balance experiment. But we'll be essentially isolating sand from a sand and salt mixture using filtration. And then we'll be reweighing the sand to kind of determine how much sand was in the salt and sand mixture in the first place. And our final experiment then for this Saturday coming, is the water of crystallization. Okay, so I won't go into that now. I'll go through that in much more detail when we're in the lab. But that's essentially using our empirical formulas that we've covered in lecture 4, and also a lot of the kind of mass to moles conversions that we've been practicing over the last couple of weeks. So everything that we've kind of covered so far, you'll see firsthand where it comes in a lab setting. So does anyone have any questions on the lab practical? So I will be in touch. I suppose I will be in touch during the week just to confirm what lab we'll be in, as well as same kind of directions on an email. We'll be on the science corridor somewhere. I'm just not sure of the exact lab yet, but I will send an email out during the week just to confirm where we are. But they will be 9 to 5.
Do we need to bring like pen and paper or a laptop for recording anything, or?
So the way we'll work it is that you'll have worksheets in the lab that you'll have to submit through Moodle at the end of them. Okay, but I will have kind of printed worksheets done for you for each experiment. So ideally what you do is that you'd fill in the information during the lab, and then there'll be blank templates on Moodle that you'll fill in using the laptop at home, and then you'll just submit it online then.
Okay, perfect. Are we allowed to bring in, when I was doing something Moodle had to be allowed into the lab, they were saying like no laptops or phones allowed in. Is that strict, or?
So that would be fairly strict, because we can't have, if particularly when we're working with the acids and bases, we can't have phones out in the lab, and it's also going to cross contamination when we're wearing gloves. You can bring your phone with you and your laptop, but we just use them outside of the lab on the day.
Oh yeah, no problem. That's fine.
But like if you need to take a phone call or you need to answer a text or whatever, like all you have to do is just step outside the lab door.
Oh no,
It's
yeah, I just wanted to make sure if I should bring it up. That's perfect. Thank you.
Oh yeah, you can bring it with you. We just don't have it out on the desk or
Yeah,
in
I get
use
you.
during the lab.
Perfect.
Yeah. So I think that's everything for now, guys, just apart from the actual room we'll be in. But as I said, I'll be in contact during the week with you for that. In terms of lab coats, if you're not planning to buy the lab kit, and again, I'll double check the stock for you during the week. If you're not planning to buy the lab kit in SETU,